This is a video on section 2.2 in calculus, talking about the slope of a curve at a point. So we've all talked about for several years in math the slope of a line, which is thought of as the rate of change. For 1 unit increase in the x value, how does the y value change? Well, what if I was more interested in, and certain, as we all know, a lot of behavior cannot just be represented as a line and is not linear. So what if we have a curve? How can we talk about a rate of change there? And that is the first part of calculus, and that's when we talk about differentiation. So when we talk about a slope of a curve at a point, we're going to look at the slope of a tangent line to a curve. So we've done tangent lines to circles before. And I have this circle here, and a tangent to a circle means it's a line that touches the circle at exactly 1 point, or intersects the circle at exactly 1 point. And if we kind of really magnify and hone in on a tangent line and blow it up, it looks very similar to kind of what one would call the steepness of the curve there. So it's quite a good measure for the rate of change of a curve at a particular point. The problem becomes is, how do you find a slope if you only have 1 point? And that's what we're going to get to today. But going back to the slope for a second, once we have the slope of the tangent line of a curve is actually called a derivative in calculus. So so you've probably heard that word before. It's a big part of calculus. And so again, if we can find that slope and we've got a point, then we can even find the equation of the tangent line there. But back to slopes. Again, slope, as we found with lines, we really need 2 points there. So first we talk about finding a slope of a secant line. And a secant line is a line that goes through 2 points. And if we look at, let's take another point here on this curve. So I have my point xy that I'm interested in finding the equation of the tangent line, right? The tangent line would hit it in exactly 1 point. But as the issue we just talked about is the fact that we need more than 1 point to find the slope. So let's make up this point Q. And so if I were to look at the equation of the secant line, then I would be able to find a slope through the 2 points P and Q. Let's give Q some coordinates. So we just said P is xy. Well, Q, let's label Q x plus h, comma, and we plug it back in to the function. It'll be f of x plus h. So why am I labeling it that? Well, let's call the distance between point P and Q h, the horizontal distance. So that's how I got the x coordinate of Q to be x plus h. And you're going to see why we're doing that for now. Okay, so then we can find the slope of the line connecting P to Q. Because remember, a slope is equal to change in y over change in x. So if I look at the y of Q, it'll be f of x plus h minus the y of P, which let's just label this function f of x, since I'm already working with that, minus, so the y of P would just be f of x over the x of Q is x plus h, and the x of P is just x. This hopefully starts looking familiar here. F of x plus h minus f of x all over h. Well, this happens to be what we worked on in the first unit and called the difference quotient. We had no idea back then what it was, but we were just working on applying it and simplifying. Well, now it's going to have huge significance. Okay, so let's do a little bit of exploration with a specific example, and then we're going to generalize. All right, so let's go to the next sheet here. So we want to find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. Okay, so we know if I were to just graph y equals x squared, we want to find the slope, and let's just call this 1, 1. We want to find this slope of the tangent line, again at 1, 1. All right, so to do this, we're going to kind of investigate and come to a conclusion here on what it is. So to do that, we're picking different values of q, and so that we'll have 2 points and find the slope of the secant line. So let's do one together, and then you can fill in that, then you can pause this and fill in the rest of the table. So we already know p is 1, 1. Maybe I'll write this up here. So p is 1, 1. Now, if I want to find the slope between p and q, if q is 1.5, then I would say, we're just doing this. The slope for pq would be the change in y. So if I plug 1.5 into y equals x squared, it would be 1.5 squared minus plugging, we already know the y coordinate of 1. It's 1 over the change in x, 1.5 minus 1. And this ends up being 2.5. So that's what I'm first going to put into the table. And you would do the same. Let's just do one more. If we did 1.1, it would be 1.1 squared minus 1 over 1.1 minus 1. And that will get me 2.1. So you can pause this and fill in the rest of the table. And then when you come back, I will have filled it in too. Okay, so I'd have 2.1. 2.001, and then when I put in 0.5, 1.5, 0.9, 1.9, 0.99, 1.99, and 1.999. So notice the Q values we put in this upper table here. The Q values were getting closer and closer to 1 from the right side or from above it, and this lower table, the x coordinate of the q was getting closer and closer to 1 coming from below it or from the left side. So as q got closer and closer to p, in other words, as the distance between p and q got smaller and smaller, it looks like the slope is approaching 2. So what does the slope appear to be? It appears to be 2. All right, so if we've got a slope of 2 and we know our point is 1, 1, then the equation of the tangent line is, I'm going to use the point slope form, so y minus y1 equals mx minus x1, and then I can solve for y if I wanted to put it in kind of a function form. So y equals 2x minus 2 plus 1 would be 2x minus 1. So that's the equation of my tangent line at point 1, 1 for y equals x squared. So clearly, though, we don't want to do this table every time we have to find a slope of a tangent line. So let's think about if we can generalize. So let's go back to what we talked about on that first page at the bottom when we had some general coordinates of q as x plus h comma f of x plus h. And we said that the slope of PQ was equal to change in y over change in x, which is f of x plus h minus f of x over x plus h minus x. And we saw that the denominator, the x's are going to cancel. So this becomes just our difference quotient. And look at what we did at the table below. We made the distance between P and Q get smaller and smaller. And when that happens, remember what we labeled as the distance between P or Q on the first page. It was H. So we want to see as H gets closer and closer to 0, what does this become? And what does this difference quotient become? In other words, as the distance between the points P and Q gets smaller and smaller, the secant line is going to get closer and closer to actually being the tangent line. And that hopefully will give us our slope. So this 3-step process is how we're going to calculate the derivative or the slope of the tangent line of a particular curve. All right, so let's summarize it. So first you would calculate the difference quotient, and then you let h get closer and closer to 0, and that will give you your derivative of your slope of your tangent line. And some notation derivative, if the function is f of x, the derivative we call f prime of x. We use that little quotation up in the top, as you can see here. Or sometimes we use, I kind of went over it. Or sometimes we say dy dx is the derivative of y as it relates to x, or in terms of x. Okay, so it says apply the three-step process for finding the derivative of f of x equals x squared, and then what is the slope of the tangent line at x equals -3. Okay, so first we're going to do the difference quotient. And then we'll see what happens as h goes towards 0. And we know, remember, we did this by inspection with, when we had x being 1 in the previous. We did it by inspection using the table, but now we're actually going to use the difference quotient, and we have a different point here. So the difference quotient is, as we just said, f of x plus h minus f of x over h. So we're going to apply it for this function x squared. So x plus h squared minus x squared all over h. Let's see what we get. We get x squared plus 2hx plus h squared minus x squared all over h. Remember, in the first unit, we would need that h in the denominator cancel. That kind of gives us an indication that we were doing this correctly. And so the x squareds go away here, and I actually can factor out an h from the top. So I'm left with 2x plus h over h, or 2x plus h. Now, as h goes to 0, this derivative, I'm going to call it f prime of x, ends up just being 2x. That's the general form of the slope of a tangent line of f of x equals x squared. Now let's find it specifically when x is -3. So I'm going to say f prime, or the derivative of f at the point x is -3, is going to be equal to 2 times -3, or -6. Okay, and this brings us to what we're actually doing, the limit definition of the derivative. So if the derivative exists, and we'll talk about that more in another lesson, then this derivative is equal to the limit. In other words, the limit means what is this quantity here, in this case the difference quotient, approaching as h gets closer and closer to 0. That's called the limit. What is something approaching as something else approaches a different number? So as h is going to 0 in this difference quotient, what is the difference quotient approaching? It's exactly what we just did in example 2. Okay, so use the limit definition of the derivative to find f prime of x if f of x equals -3x squared plus 2. Okay, so let's do this here. So f prime of x is equal to the limit as h approaches 0. So we're just seeing, does our difference quotient approach anything as h goes towards 0? And remember, we do f of x plus h first. So -3x plus h squared plus 2 minus the function itself. So minus -3x squared plus 2. I always put those parentheses just to remind myself I've got to distribute that negative. Okay, so this is the limit as h goes to 0 of -3 times x squared plus 2hx plus h squared plus 2. Then I'm going to have plus 3x squared minus 2. All right, and I'm doing it step by step just to make sure I don't mess up any negatives. So the limit as h goes to 0 of -3x squared minus 6hx minus 3h squared plus 2 plus 3x squared minus 2 all over h. All right, let's see what goes away. The x squared, 3x squareds are eliminated, so are the 2's. And so we're left with the limit as h goes to 0 of negative 6hx minus 3h squared all over h. And if I factor out the h from the numerator, I've got h negative 6x minus 3h. Then that h in the numerator and the denominator go away. And so I'm looking at the limit as h goes to 0 of negative 6x minus 3h. And now if I plug in 0 for h, I'm getting negative 6x. And so that's going to be my derivative of f of x when f of x is negative 3x squared plus 2. Okay, let's do just 2 more before we example 4 and 5, and then you can look at the homework. Okay, so example 4. Use the limit definition of the derivative to show that if f of x is mx plus b, so the slope-intercept form of the equation of a line, then the derivative is m. So we would expect this. It should be this, right? That's the one thing we definitely know. We know that the slope of a line in this form is indeed m. So let's prove it. So f prime of x equals, so limit as h goes to 0 of, when I do f of x plus h is m x plus h plus b minus mx plus b all over h. So this will be the limit as h goes to 0 of mx plus mh plus b minus mx minus b over h. And this is going to be the limit as h goes to 0 of the mx's go away, the b's go away. So mh over h, which is the limit as h goes to 0 of just m, which of course is just going to be m, because when you plug in 0 for h, well, there is no h, so you're just left with m. So that proved for us that that indeed was, which we already knew, that the slope of a line is m, or the coefficient of the x. Okay, so let's do one last one. We're going to find f prime of 2, so the derivative of f of x at x equals 2 when f of x is x cubed. All right, so let me expand this a little bit. All right, so f prime of 2, so instead of doing x plus h, I'm going to do 2 plus h, because I know that x is 2. So it's going to be the limit as h goes to 0 of 2 plus h cubed minus f of 2. So f of 2 is going to be 8 all over h. So again, what I'm doing here, maybe I'll show you above, instead of doing the general f of x plus h minus f of x over h, I'm just doing the limit as h goes to 0 of f of 2 plus h minus f of 2 over h. Again, because I know, and this is what my f prime of 2 is. Because I want to know, I know what I want the derivative specifically at x being 2. Okay, so let's keep going here. So 2 plus x cubed, not exactly fun. So I know 2 plus h squared is going to be 4 plus 4h plus h squared. And then that's going to have to be multiplied by 2 plus h minus 8 over h. Okay, so this is going to be equal to the limit as h goes to 0, h goes to 0 of, let's see, 8 plus 4h plus 8h plus 4h squared plus 2h squared plus h cubed minus 8 all over h. So this is the limit as h goes to 0. So we've got the 8's going away. And let's see what we have. We have h cubed plus 6h squared plus 12h all over h. So if I take an 8, not an 8, an h out of every term in the numerator, and it cancels with the h in the denominator, I get h squared plus 6h plus 12. And now when you plug in 0 for h, I'm just left with 12. Okay, so how to find the slope of a tangent line in general for a particular function and at a specific point using that limit definition of the derivative, which involves the difference quotient.